Section 3.4, related rates. All right, this is going to be a more difficult section here, so you're really going to have to just be patient with the homework and so forth. But keep at it, eventually you'll get it. All right, so let's describe what we're going to be doing in this section. All right, let's suppose I'm playing a game, and it's got some kind of timer, maybe an hourglass timer or whatever. And I'm only looking at, okay, the hourglass have the other part right there, but I'm only looking at the top part that's got sand in it, okay? It's got sand probably to the top of it at the beginning. You flip that timer over, then you got to answer questions real quick, okay? What's going on? The height of the sand is here, then it goes down here, then it goes down there, then it goes down there, and eventually runs out. But what does the sand do? It's going down, the height of the sand is going down, kind of slow at first, and then once it gets towards the bottom, since there's less sand right there, it starts to speed up, right? So the rate at which this height of my sand is at differs, right? It's going slow first, then it speeds up as it gets closer to the bottom. So with related rates, we want to find, okay, how fast is the height of that sand changing whenever the height is up here, let's say at 2 inches, okay? How fast is the height of sand decreasing whenever the sand is right here at 3/4 of an inch, and so forth? Or how fast is the sand, the height of the sand changing, decreasing whenever my sand is here, okay? So a lot of time we look at it as a derivative, change in h with respect to time. How fast is h changing with respect to t? All right, same thing, you're gonna look at tanks here that'll have water in them. Maybe the water's running out, so the height changes. Also, maybe you're filling up a tank that doesn't have a hole in the bottom. And what happens? It fills up quick at first, and the rate slows down at which it increases. All right, and a ladder. Let's suppose you have a ladder leaning up against the wall, but you don't put the ladder upright, and it slides, it falls down, okay? What happens when something falls? It starts falling slow, and then it speeds up, right? So we can look at this height, how it changes with respect to time, or the derivative of height with respect to time. Change in height with respect to time. We could also look at how this angle is going to be changing. When the ladder's falling like this, how's this angle going to be changing? Well, it's going to be decreasing, right? But it's going to be decreasing at a faster rate whenever that ladder goes closer to the ground. So we would want to know the rate at which theta is changing. Okay, so we can find it whenever theta is like 45 degrees. We can find it when theta is 30 degrees and so forth. But that's the big picture of what we're going to do here. All right, so let's start out very basic. Very basic. All right, let's think about section 3.1, implicit differentiation, okay? We were told if y is a function of x, and I'm taking the derivative with respect to x of y to the fifth, what do I do in this case? Remember, if that variable is different than that one, I take 5 times y to the fourth, but then I need what? Times dy over dx, right? All right, same thing if we have the derivative with respect to x of y to the seventh. How do I handle this if y is a function of x? Since these variables are different, I say 7 times y to the sixth, but I still need dy over dx, because I still need the derivative of the inside, because y might be equal to x to the fourth minus 3x, okay? So that's what would be in there. So I still got to take the derivative of the inside. All right, now, we don't always have to deal with y and x. What if I wanted this? What if I wanted the derivative with respect to t of y to the seventh, where y was a function of t? I would do the same thing. I would say this is 7 times y to the sixth times dy over dt here. Same thing with this. Suppose I want the derivative with respect to t of x to the 19th. How do I do that? If x is a function of t, I would say that's 19 x to the 18th times dx over dt. dx over dt. How about this? The derivative with respect to t of z to the 8th. How would I write that if z is a function of t? I'd write that as 8 times z to the 7th times dz over dt. And that's the kind of stuff we're going to be dealing with first of all. Let's look at our first example we have here. All right, so time for an example. Let's look at this first example. Our example is going to say, what if we have y is equal to 3x plus 5, and I'm told, given that dy over dt is equal to -1, find dx over dt when x is equal to 0. Now, sometimes they give you extra information, but that's fine. So let's work this problem. So what do I have here and here? I have the derivative with respect to t. So what I'm going to do is take the derivative of each side of this equation with respect to t. So I'm going to have d over dt of this y is equal to d over dt of 3x plus d over dt of that 5. All right, now how do I write this? I just write this as dy over dt. It's equal to, how do I take the derivative of this? This 3 times dx over dt, right? And plus what? 0 right there, because the derivative of a constant is 0. Now, they tell us what dy over dt is. It's -1. It's equal to 3 times, how about dx over dt? That's what they want me to find, so that's unknown. Plus 0, I don't need to put anything. Now, they gave us x was 0, so if I had an x right here, I would sub in 0, but I don't. Let's solve for dx over dt. So divide both sides by 3, -1/3 is equal to dx over dt. There we go. I found dx over dt when x was 0. Actually, when x was anything. Our next example, we're going to have 4x squared plus 9y squared is equal to 1. And they say, given that dy over dt is equal to 8, find dx over dt when we have the order pair x comma y equal to 1/3 comma negative square root of 5 over 9. Not a pretty point, but it's a point. All right, so what do I start out with here? I start out with my equation, 4x squared plus 9y squared is equal to 1. Now notice, each derivative is with respect to t. So I'm going to take the derivative of both sides of this equation with respect to t. So I have d over dt of 4x squared of the first term plus d over dt of my second term, 9y squared, is equal to d over dt of that 1. All right, so what does this give me? This gives me 8x to the first times, remember this variable is different than that one, so I need dx over dt, right? Plus, how about this part? That would be 18y times dy over dt. Derivative of a constant is 0. Verify that for yourself. Don't just follow me. Don't just write down what I'm writing. Make sure it makes sense. All right, so let's fill in some stuff, okay? We have 8 times x, but what are they telling me x is in this case? It's 1/3 times dx over dt. Did they ever tell me what dx over dt is? No, that's unknown. So I just write as dx over dt. Plus 18 times y. They tell me what y is. They said y is this nasty number, right? negative square root of 5 over 9 times dy over dt, which they tell me that is what? 8. So I'm going to replace this with 8 is equal to 0. Now it's just a matter of solving for dx over dt. So here we have 8/3 dx over dt minus, because positive times a negative, right? 2 square roots of 5 times 8 is equal to 0. Or I can say 8/3 dx over dt minus 16 square roots of 5 is equal to 0. Now let's go ahead and add 16 square roots of 5 to both sides. So we'll get 8/3 dx over dt is equal to 16 square roots of 5. Then we multiply by the reciprocal. Multiply by 3/8 on both sides. So dx over dt is equal to 3/8 times 16 square roots of 5, or I could look at it as over 1, right? 8 divided by 8 is 1, 16 divided by 8 is 2. So dx over dt is equal to 3 times 2, which is 6, times the square root of 5. And there we go. We found dx over dt when x and y were these values.